student presentation on a topic for the class, and Lily's presenting on testing for normality.
So the first question is kind of why would we test for normality? And so kind of as we talked about for hypothesis testing and confidence interval, we have a set of assumptions. Some of those are independent, and if you have like double two sample, then it could be, is the variance equal to 2? But then we also talked about the yi, or the sample, should be normally distributed. And then if we look forward, when we talk about simple linear regression in chapter 7 and 8, we'll talk about this normality assumption, and it almost becomes more important here, especially if you have outliers or if you have a small sample, then it's important to make sure that your distribution is normal. But it's even more important when you're trying to predict using your simple linear regression model, because you create the model based on the assumption that your data is normal. So if it's not, then your prediction won't be accurate. So the methods, or there's multiple methods for testing for normality, but I just picked 4 to look at. So you can kind of look more informally at the histogram, look at the shape. Is it bell-shaped? Is it symmetrical? Are there any outliers? And then you can also use a QQ norm plot to graph it. And what this does is it plots the observed values of your of your sample, along with expected values, assuming it is normal. And then if you see a straight line, straight 45-degree line, then you can assume that your distribution is normal. And then some of the more other tests that you can do skewness and kurtosis. And so for skewness, you can look at how long of a tail it is, and your skewness should be around within -2 to +2. And I'll show the statistic for that on a different slide. And then kurtosis is a similar thing, but it looks at how much of your distribution is in your tails and compares it to what a normal distribution should have in the tails. And these statistics will be on a different slide as well. And then one test that you can do pretty easily in R is the Shapiro-Wilks W test. And so it has a null hypothesis that the distribution is normal. And then the alternative is that it's not normal. So if the p-value is significant, then you reject the normality assumption. And if it's not significant, then you can assume that the data is pretty normal. So to look at different examples, I just picked this one data set. This was fertility and socioeconomic indicators from 1888. And then just to start, I kind of looked at all the different variables. There are 6 of them. And in order to kind of get a better understanding of how the different tests work, I picked 4 that have different shapes. So those are fertility, agriculture, education, and Catholic. And most of these are percentages of the total population, but fertility is just a common standardized fertility measure. So for fertility, I started by just doing a histogram and noticed that it looked roughly bell-shaped and it looked roughly symmetrical and didn't have any outliers. And so then I turned to the QQ norm plot, and as you can see from that, most of the points are roughly on the line graphs, which is the QQ norm line, but there are a few on the left that fall below, which might indicate some skewness, which you can kind of see over here. But I wasn't too concerned with it. And then I did some more formal testing and looked at the skewness, which this is the way you calculate it. And I got -0.4456, and so that didn't seem too concerning, but in order to further test it, I simulated multiple, like I think 1,000 times or 10,000 times, in order to, assuming that the distribution was normal, with the sample mean and the standard deviation from this sample. And then kind of like we did in the permutation test, I ran that 1,000 times to then get a histogram and graph it and plot where the p-value or the skewness we observed is, and then to calculate in a p-value of skewnesses that were more extreme than what we experienced. And I got a p-value of 0.15, and so that's greater than a significance level of 0.05, and so I failed to reject normality due to skewness. And so then for kurtosis, I did a similar thing, but I used a different, I obviously used the kurtosis statistic. And normally it's centered at 3, but I wanted to be able to compare it as a mean of 0, and so I just subtracted a 3 at the end. And this kurtosis was negative 0.8855. And again, that didn't seem too unreasonable, but I did the same like simulation thing again, or sampling thing, and got 0.73. And so again, I failed to reject due to kurtosis. And then in R, you can just do the Shapiro-Wilks W test, and it's with that I got a W statistic of 0.97 and a p-value of 0.35. And so again, I just failed to reject. So then I looked at this one because it didn't quite look bell-shaped, and so I wanted to see if there was a difference in what the test would indicate. And so you can see by the QQ norm plot that it's a little more wavy, indicating that it's maybe not quite normal. But it didn't look too bad. And then when I did the same thing for skewness, I ended up failing to reject normality, and failing to reject kurtosis, and failing to reject the W test. And so even though it doesn't necessarily look bell-shaped in the original histogram, none of the tests actually rejected the assumption. But as you can see here with the histogram, we can really tell pretty easily that there is a skew to the right. And it's pretty obvious to see that in the QQ norm plot that there's skewness, because with skewness you can see like a curve in the QQ norm plot, which you see here. And so it doesn't look normal. And the skewness, kurtosis, and Shapiro-Wilks W test all also showed that you should reject the normality assumption. Pretty obviously too, since the skewness and kurtosis that we saw wouldn't even be on the histogram we would expect if the distribution was normal. And then lastly, for the Catholic, this one was kind of like, it was kind of, I don't even know what to call this.
Bimodal.
Okay, bimodal. And so I wanted to see what the QQ norm plot would look like. You can see that it has like a S shape. And then I think the most interesting thing I found here was that skewness failed to reject normality, probably because it's not really skewed one way. It has like large clumps on both sides. But that kurtosis would reject it because you have way more in the tails than you would expect for normality. And then the Shapiro-Wilks W test confirmed that you should reject the normality. So kind of in conclusion, it's as noted in the textbook, the hypothesis test and confidence interval and simple linear regressions can remain like strong without having the assumption of normality. But if there are outliers in your data, or if the sample size is too small, or if you're trying to predict with your model, then it's really important to make sure that the normality assumption does hold. And again, there are more ways that you can test for normality, but this is just a sample of them. And then, as we saw, not every test will result in the same output depending on what the sample looks like.
Great. But any questions about it? So it was, I mean, it's really interesting with the Catholic example, right? That you do a test, it's one statistic and it doesn't reject skewness because it's not skew, but it's certainly not normal. So anybody else need a handout before we go on? So I'll put the presentation up, and Lily provided the code as well if you wanted to see some of those computing things. So in there was a sample estimate of skewness, a sample estimate of kurtosis, and some courses would cover that, but you could look at that or ask about those or if they're particularly relevant for yours. The Shapiro-Wilk is one test, and there's a whole bunch of other ones that people have done. And a lot of those other ones that are out there are motivated by, well, the Shapiro-Wilk or one of these others doesn't pick up on this feature that's not normal. Right? maybe gaps between data points rather than, you know, overall spread, or, you know, it's just different aspects, and so people come up with different things that are more sensitive to some departure or a couple departures, and so there's different ways of testing, and it's kind of a slippery, you know, it's kind of a sliding scale, you know, it can be very non-normal and distort a test, or not as non-normal, you know, kind of non-normal but not really distort the test. It kind of depends on what you're using it for. So that's what I mentioned. Great, great. The next one of the presentations is posted along with the assignment, and it's about what impact does non-normality, maybe transforming data, have on ANOVA. So it kind of takes a couple things that we did from the previous two, perhaps to some degree, but then, you know, you do ANOVA on the original scale or maybe on a log scale. In cases, you get different testing results. And the third person by the randomization is Annie, gets to do it for next week. So I think it will tie in to the other two, but also the current material that we're doing towards the homework. So, but any questions about? So we're going to look at contrast in ANOVA and multiple testing in ANOVA and kind of review the ANOVA table. So in the ANOVA table that we did, there are I groups, N sub I observation in group I, and so N is our total sample size, the sum of the NIs. And we did a number of statistics that we can put together in a table for our kind of standard presentation. There are our groups. Sometimes these are called, if it's a randomized experiment, these might be treatments. Sometimes it's between, like between groups. Or R, in many computer programs, in their output will put the variable that's defining the groups there. So diet, or judges, or whatever you're doing, right? And then there is error. R calls it residual. So the residual after you take out the mean. And sometimes it's called within groups. Different fields and different applications will have slightly different terms that are there. And of course, this can be total of some things. One column is degrees of freedom. If there's I groups, we get I minus 1 there. If there are N observations, we get N minus capital I there, and those two things add up to N minus 1. So if you just had one big sample of N observations all together, and we're calculating a variance, the denominator we typically use is N minus 1. There are sums of squares. Right? So sum of squares groups, or sum of squares error. These two things actually add up to sum of squares total. Some books call it SS tot. Particularly if they call this one treatments, and that's SST, then they might call this one SS tot. But it's always in the same place. And so this was a sum over the groups of the difference between the group average and the overall mean. And this one was a sum over I and then a sum over J. Subscript I is there, of the individuals minus their group average squared. So those deviations from the group squared. And if our null hypothesis is true, these should be pretty small, and this is whatever it is. You know, there's just natural variability in the groups. Mean square is a sum of the square of groups in this case divided by its degrees of freedom, and sum of the squares error divided by its degrees of freedom. And the mean squares don't add up, so I usually don't put that one there. Right. This one is our pooled estimate of variance, mean square error. And then our F ratio is the mean square for groups over the mean square error. And Right, so that's the table we get, right? And we're going to use that to test the hypothesis that the means are equal, right? Versus some difference somewhere. So that's the basic table that's out there. On the next page, I'll write the hypotheses. Once you've written the notation with subscripts about 100 times, then it's, you kind of whip through it. In any case, so we want to test the hypothesis that all the mu sub i's are the same. Right, no difference in means. Alternative hypothesis that can be that some mu sub I is different. You might phrase it as at least one mu sub I is different. They might all be different from each other, or like in the case of the trials, we're interested in is the judge Spock different from the rest? But they could be arbitrarily different. And so under the null hypothesis and normality, and independence, right? So there's a few assumptions in there. The F statistic, that's mean square for the groups over the mean square error, is distributed as an F distribution with the degrees of freedom given by the groups and errors. So I minus 1 because that's in the numerator, and n minus capital I because that's in the denominator. And under the null hypothesis, we expect a statistic. Sometimes I put a statistic on here to emphasize that that's the F from the data versus the F distribution. The null hypothesis is true. We expect all those means in the sample to be close together, and then the numerator, the mean square groups, to be kind of small. And so we expect F's to be small, and expected value under the null hypothesis is about 1. So we're going to reject the null hypothesis. Page 0, if the F statistic is bigger than our F cutoff value from that distribution at the 0.95 cutoff. So if we have this F distribution that's positive, everything's squared, so the F distribution, right, so if we're up in this tail, right, this is our region where we rejection region, our F statistic ends up being out there, accounting for our degrees of freedom, then for its shape, then we reject. And that's the basic thing. And so both of the examples that we have in the book, we end up rejecting because there are some differences. You see those in graphs, and it works out with the sample sizes. Sometimes you might see differences or things that look apparently different, but if some of the groups have big variances and sample sizes are small, it just might not work out to be overall significant. But often if you can see what appears to be a pretty big gap, then there's. On the other hand, if you have large sample sizes and there's a little deviation, but the groups overlap a lot, it might still be enough evidence to say it's significant. So actually calculating the statistic gives you something beyond just looking at the graph. So say if you don't reject the null hypothesis, that's about all there is to do, right? There's no difference. You need to go back and figure out, well, why wasn't there a difference? Are my sample sizes small? Are some of my assumptions? We might look at those. We'll talk about a little bit more of that on Friday. Maybe some of those didn't hold. Maybe there's outliers that made the variance very large, so I didn't end up getting a significant result. Maybe my actual application, like I didn't run the study long enough. Maybe my medical treatment didn't make that much of a difference in 1 year. Maybe in 3 years or 5 years it would have made a difference. Maybe the drug or treatment wasn't strong enough. Just giving people a brochure about healthy living might not do too much, but putting them in a classroom and sending them text reminders, maybe the treatment has to be stronger to get an effect, even if your idea is good, maybe the implementation didn't do it. So if it doesn't reject, you're kind of back to that, okay, what's going on? I need to rethink things. Unless we're really hoping there was no difference, and then that's okay. On the other side, some people could do ANOVA and do things to make it less likely to get a significant result, right? So if you wanted to test the impact of lead exposure on children, how would you avoid getting a significant result if you're from industry and don't want to be found guilty of doing something bad, right? Small sample sizes, measure the effect for a very short period of time, right? Very imprecise measures of things, right? Not that people would intentionally do something like that to try to do something bad to avoid being guilty, but the things that could help you make a significant result. One way, if you don't have big enough sample sizes, it makes it harder to detect even a true difference. Right? Let's say you do reject. Right? Suppose you reject the hypothesis, and you reject, and then you conclude there is some difference in means. Then we want to know where the differences in means are. Characterize them, go a little bit further in evaluating the different groups. Right? So we could look at, one mean versus another mean. For instance, it's an I, a little I prime that's in there. Then you'll just make this L2. We use J for the other indexes. I'll just make it L. So it's just in some particular group that you're interested in there, right? Or we could estimate the difference between two groups. Y bar I minus Y bar L. We could see if that difference looks, right? We could also look at the graphs of the data. Maybe particular groups would look different. Right? If we have equal variances, as we do in the ANOVA model, right? We want to estimate, well, let's see, I should say that the variance of this thing, the variance of Y bar I minus Y bar L, if variances are equal, I'm going to get this out of order, there'd be an overall variance, and then there'd be 1 over the sample size for the first group, plus 1 over the sample size for the second group. So what I'm getting around to saying is we want to look at the distribution of sample differences. We're going to assume that we're going to do a t-test or a confidence interval based on a t-distribution for this thing, and we need its standard error. Right? So its variance is sigma squared with the two sample sizes, and this common variance sigma squared in there is important. Right? In the ANOVA context, right, if this was just two samples, if we just had two samples, we'd have to do our pooled estimate based on two samples. But now we have I samples all from a distribution with the same variance. So we could use them all together to estimate this. So our estimate of this thing is our pooled one from ANOVA, which is also called our mean square error. Right? Sigma hat, or SMP, the square root of that, some call it the root mean square error, or RMSE. Right, you'll see it's short. So out of the ANOVA table, we get, at those initial computations, we get an estimate of that. Right? And so we're going to do, say, a confidence interval for the difference, mu sub I minus mu sub L, Y bar I minus Y bar L, and then we're going to plus or minus a margin of error. We're going to do t-value with some degrees of freedom, and 0.975, so we do 95% confidence interval for one mean. And then this S sub p, 1 over n1 in I plus 1 over in L, square root. Right? And the question is, which degrees of freedom do we get to use in there? If it was only a two-sample test, and we only had two groups, we only could use N1 plus N2 minus 2. We would use that degrees of freedom from our two sample procedures. But because we've estimated this based on the entire data set, right, we actually get to use the degrees of freedom from that entire data set. That's the degrees of freedom associated with estimating that variance. So we get to use a bigger degrees of freedom. So from ANOVA, we use degrees of freedom that is n minus I, which is the sum over all the groups of n to the I minus 1. They all contribute. The n minus I is going to be greater than or equal to, you know, the thing. This is the two sample degrees of freedom that we would have. And the consequence of that is that the t distribution, the 975 cutoff for this one, with the larger degrees of freedom, is going to be smaller. Right, than this one. So our t value, our t multiplier, is smaller in the ANOVA context than it would be in just a two sample t-test, right? So we have a bunch of groups, and the pooling assumption, you know, the variances being equals is roughly reasonable, right? Then we get a smaller interval, right? Which is nice. Put that there. If it's two sample, if there's only two groups, then it doesn't matter. 2t test is going to be the same as the ANOVA two groups. So that's good. But you know, something goes on, right? We've chosen these 95% confidence or level 0.05 test so that we don't make too many mistakes. Right? If the null hypothesis is true, we don't want to reject it. Right? So if a particular pair of means, group I and group L, if those means are the same, we still don't want to reject it. Right? But if we're doing a bunch of tests, right, if we have I groups, we have what's called this multiple testing issue. Right? If we have I groups, there's I choose to, calculated as I times I minus 1 over 2 pairs of groups. So with the 7, you know, if we want to test all those judges, 7 judges, or 6, there are 6 diets, right? So 6 choose 2 is 15, so you're doing 15 different tests. And if you do them all at the 5% significance level, there's actually a greater error possibility than, you know, 0.05, right? This one could make an error, or this one could make an error, or both of these could make errors together, and so the sum of any error is greater than 5% if you do them each at 5%. So we still want alpha 0.05 to be probability of an error when we reject an H0 when it is true. Right? We don't really want to reject the null hypotheses where there's no difference. So there's a bunch of people who have thought about, well, how can you do that, right? How can you do all the tests so that kind of the family-wise or the overall error rate is small, right? One approach is called Bonferroni. Test at the alpha equals 0.05 divided by the number of tests you're doing. That is, reject, in the case of the diets, I equals 6, and 6 choose 2 is 15. So in this case, we would reject H0, a difference in means. Mu, so if our t statistic for testing is greater, the absolute value of it, because it's two-sided, is greater than the t, now our degrees of freedom is n minus I still, but we would use 1 minus our 0.05, instead of just dividing it by 2, which we do for a two-sided test, right? That we get that. We would also put a 15 in here. So make that tail area you have to be out in quite a bit higher. Right? And we'll see how to do that on the computer shortly. But anyway, you adjust that to make it harder to reject. Yes?
What is the first word before the I equals 6?
Oh, this isn't the dyad example.
Oh, okay.
So this is the number of tests, and so in this case, it's the 15 tests for that particular example. So this is going to be something like it's going to be much more than 0.975. It's 0.99 something. So you have to be out there pretty far. So if you do reject then, you're sure that you've not made the testing with a significance level, any of the tests as a composite, any rejection with errors over 0.05. It's more stringent. Okay. But there's a number of other things that get done. So let's look at an example of that. So that's Lily's code, which you can press, you can look at that. So for class today, there's our code that's there. That one. And, this one. So we're using these the old data sets from before, the diet, and environment, nothing's in there. Let's see. It doesn't like my thing, so let me just open it. I loaded in on my computer downstairs, and so it's ready. All right, so anyway, now I can attach those things. This is what the data looked like. Right. For these different diets, there's a reduction of calories, there's a 50 or 40, and then there's a low protein one, and there's a way to make this, so you can see those things. I think LAS is 2. Right. You can change the orientation of those axes, so you see these things. So there's a low protein one, and the 40 is even smaller categories, and I think this was the control. Right. And so is there a difference? If we run the ANOVA command, it gives this output that you have there. Degrees of freedom, there were 349 overall. So diet is the group in residuals. Sum of squares, mean squares, and the F value is absolutely enormous, and the P value is quite small. So there is a significant difference. There's no question about that. Now we ask, where is it, right? Which of the means are different? So you might guess that the NP is quite different from those, and the NN is quite different from those. Maybe these two are different. I don't know. You know, maybe these two. It's a little bit up in the air whether these 4 top ones are going to be different from another. Right? Which diet has the biggest impact? So if you you can calculate the mean for each group. This does it. You know, we split the lifetime values. Those are the outcomes, the y variables by the diet groups, right? And then so that's a list with them broken out by the different 6 groups. And then this apply to that list, create, these are the different averages. So in 85 had an average of about 32, this had an average of about 45, and things like that. There is a pairwise test, t-test option in R. Where does that run? That's where there it goes. And so it gives you the output you have there. So pairwise comparison using t-test with pooled standard deviation. That's what we want. And it just gives p-values. So testing the NR40 versus NR85, right, these two, that p-value is very, very small. And this is very small, so anything versus NN5 is different. What about versus NP? NN85 versus NP, even that one's significant. These two end up being significantly different from one another. And this has used the Bonferroni adjustment. That you can tell it with different options. Right? There's a whole literature about how to do multiple testing. Right? The Bonferroni for larger sample sizes is pretty extreme, right? Just to find down there. There's ways that you can do it so that you get closer to 0.05 overall. The Bonferroni will be quite a bit less than 0.05, which is okay. You know, we don't want to make more than 5% areas, so we can make it a lot less. Is anything not rejected? It looks like the RR50 and NR40, RR50 and NR, these 3 do not look like they're rejected at all, right? And this one's not rejected, so low protein versus some of these is not rejected. So some of these 4 up here don't look any different from each other, but these 2 look different from all the others. And it's adjusted. There's help files in R. Help, pairwise, t-test in there. And it has p-adjust methods, and so if you go down in here, it says method for adjusting p-values, p.adjust. So there's a file for that. There's a little help file. And here's the Bonferroni. That's in there. But Holm is a very common one. Some of these, like Hulkberg or false discovery rate, are set up for really high dimensions. They're intended for genetic type studies where you have thousands of tests to do. And dividing by 0.05 by 1,000 gets ridiculously small. So they do something a little bit different. But if you're reading articles where they say they adjust by multiple testing, and they use a Hulkberg, or I think it's Benjamin Hulkberg, BH, or some other thing, that one of these options might be already encoded in there. And you can search on Google to find help on those, and it would be described in some books. But the Bonferroni captures the idea. So we have to do the testing at a smaller alpha level to get bigger results before calling it significant. Otherwise, we risk calling things significant, and it's just by chance because we're doing so many tests. Something's going to stick out just by random chance. But these don't. Right? Another common way of doing these things is a command called Tukey's. John Tukey was at Princeton, and he's famous in statistics for writing books on exploratory data analysis. So, box plots and stem and leaf plots, and a number of kind of just exploratory tools, plus another things in different ways of doing things. He's just kind of a creative guy, and he was involved in a lot of things in computing and software back in the 1950s. So generally interesting. So there's highest or honest significant differences, he called it. And so you run that, and it kind of goes off a little bit that bigger. So you get a few more things in there. It does all the pairwise differences. This is nice because it gives you the average difference. It gives you a lower and upper confidence interval for it, which you might like to see, and an adjusted p-value. And it uses a slightly different formulation of that. Again, you could look that up Our book mentions an idea without going into too much detail, so you could look at all those. And again, many of them are significant, but a few, like this, these are the two big ones. This was at 2 at the top. This one gets a few of, the low protein versus that was not different. But anyway, there's a few that are not different at certain levels and some others that are. Now, the book actually describes in this experiment something a little bit more specific. It's not necessarily so keenly interested in all 15 contrasts or mean comparisons. Right? It is interested in a few of these. This reduction of calories, 50 versus control. Right? And then there's a couple about at what age this is implemented, and it's 50 versus 40 calories. The 50 versus 50 with low protein. So it's interested in 5 specific contrasts. Right? So instead of adjusting for all 15 possible comparisons, right, you could make a case that if this was written up in the research, is we're going to adjust for just 5 comparisons. Right? The impact of that is that the t-values don't have to be so big to be significant. Or your t-multiplier doesn't have to be so big. So your confidence intervals can be narrower. Right? So if you only have 5, that you're really primarily interested in, then you don't necessarily have to adjust for the total possible. To do that, there are some commands for contrast and things built into R that require some packages and a little more programming, but I wanted to just look at it by hand. Right, you can do it by hand. So for instance, if you wanted to do this diet reduction of 50, versus the control. This was the control indicator. Right? You can take the differences and means of those and see what it is. About 9.6 is the difference between those. The pooled standard deviation, you can pull off the ANOVA table. Remember, the ANOVA table would have had a column for mean square, and it's actually the second entry in that mean square column is the mean square error. So the square root of that becomes our mean square error. So you can pull that one statistic off of there. And it's about 44.5 with the square root. Right? And so the standard error is that pooled one times the square root of 1 over n1 plus 1 over n2 for those two groups. And that's our standard error. Degrees of freedom, we get to use the degrees of freedom error from ANOVA. So we get our t-value. If we just do that particular one, we would get that as a confidence interval. Let's see. Let's run all these things. And we get 7.3 up to 11.9 as a difference. Now we are planning 5 tests. So somebody would bring up that you've done 5 tests. You maybe shouldn't use 0.5 level for everything. You might argue that all these are all primary hypotheses, so everyone's going to be done separately. And so that's a little bit of uncertainty in the kind of how persuasive you could argue you get to use 0.05. But somebody might, dividing by 5, use 0.01 as a test. Right? So we'd want to be greater than the 0.995 cutoff rather than 0.975. We have to be out a little bit farther. So we get a new t-value under that. And if we do our confidence intervals again, they get a little bit wider to adjust for the fact that we're doing multiple testing. But if you just went in and say, oh, I have 15 pairs, I have to do Bonferroni. There's a typo here. Value. See, that's the scripture thing. If I had been AV, the code would have run and I'd reuse values, so it would have just used the old number and I wouldn't have adjusted like that. So, right. So now we have a new t-value, and now our interval is a little bit wider. So just doing the one based on 0.975 gets you this. It adjusts for the 5 tests you plan, you get a little bit wider, and that's probably a reasonable thing to report. If you were just searching and didn't have those hypotheses stated earlier, somebody might say, well, you really need to, you're just searching through differences. So, or avoid the biggest ones. So, make a bigger adjustment to be fair and not overstate your case. So if you search through your data and find the biggest difference in pairs and do just a confidence interval for that, people are going to say, oh, you just picked the biggest one. That's not really fair. You didn't know that a priori. It's not like you did a random, you just had two groups and did one study and came up with a confidence interval. You picked the biggest one, so of course it's going to look wider, but maybe part of that's due to chance. So the 15 would certainly adjust for that type of choosing just the biggest. But this one seems a little more reasonable. And you get a little narrower confidence interval. Doesn't really change the story that that diet is better, but you know, it is more precise. So it's more valuable to state the more precise thing. So that's the nature of the kind of the comparing groups, right? You have the graphical evidence. Hopefully in the science of things you have a priori hypotheses, and then doing one method or another for simultaneous for adjustment. Makes sense. In the trials, and I said venues last time, but it's really veneers, are a list of the people who are eligible to be in juries, right? And it was, if you read the description of the context, so it was actually kind of interesting that Benjamin Spock, who was a doctor, wrote books on pregnancy and having babies and raising babies, and so certainly, yeah, that was a very common book, and I've seen it in different people's houses, right? So my wife's mother had the copy of that book, and so it was all over. But he was an anti-war activist too, so he was encouraging. He was accused of having people, resist the Vietnam draft, right? So that was illegal. I mean, you can't encourage people to break the law, right? So if you actively do that, you can be hold, and that's, it's a time of wartime, so that could be a treasonable offense or something. So, but then the people trying him were trying to get people who had a favorable view of him because of his book to not be on the juries, right? So they were excusing women, right? They can do a lot of peremptory challenges, right? If somebody comes in and has a clear bias against the, if they ask, have you heard about this in the news? Do you think the person's guilty? Yeah, they're guilty. Well, then they don't want them on the trial, right? If they come in with a preconceived idea or some other bias about them. And so they were trying to get, the lawyers apparently were dismissing women who had heard of his book because it's very popular and they would be more predisposed. So did the veneer or people eligible for sitting on the jury after this selection process exclude more women than typical with their bias? Right? And the defense was saying, we can't get a fair trial with this. You need to get a jury that includes a more balanced thing. Right? So here are the box plots, right? For, right, the last one is Spock, so this last one is Spock. Let's try that. Not that we really need to do this, but this LAS adjusts it. Yeah. So his veneer had a much lower percent of women involved, right? Across different groups. Analysis of variance for that, right? Degrees of freedom. There were, so that adds up to 45. There were 46 in all. No, yes, 45, 46 in all. Sum of squares, mean squares, the F value again is pretty large, and the P value is very small. So there is a significant difference, right? And in this case, we're really interested in, is Spock's percentages different than the others, right? So you could do pairwise. You could do this one versus this one, or this one versus this one, and so on. And most of those would be significant. But a different way to do it is to look at the contrast. Is Spock's different than the average of these, right? Because that's really the focus. In the diet one, you might do, are the kind of two typical diets different than these other? There's 2 and 4, so you might be this 2 versus this 4. And so analysis of variance, we can do these specific contrasts, right? Some people call them 1 degree of freedom tests, right? They're t-tests, but they're focused on one dimension, right? It's not any difference. It's a very focused dimension, and so you can learn a lot more that way. So here are the different means for that. I'm going to save those means here. And if we just do the S-apply thing, it has the letters on there. I just want it to be numerical values. Sometimes in R, you don't want those extra letters hanging around. You can just make it a list of numbers. A little technical R thing. And we want to test whether Spock is different. Right? So we're going to get the sample sizes for the different groups. What was the n's? These are the n's for the different groups. They're kind of small. D is pretty small. But under the ANOVA assumption, we get to estimate the variance by the pool one. So we get to take it off the ANOVA table, right? Degrees of freedom off the ANOVA table, so degrees of freedom for us is going to be 39, right? Rather than, if it was just Spock versus one of these other groups, degrees of freedom would be something like 11, right? So the T value we're going to be working with, if we had to do a 9.75% test with, say, about 12 degrees of freedom, it'd be that number, but with, 39? It's a little bit less, right? So that's, it doesn't seem like that big of a difference, but a difference of, about 4%. So your intervals are going to be about 4% wider or narrower, depending on which way you do it. That's an advantage. That's certainly an advantage. So I'm going to take the others, just being the average of the other ones. They're about 29 on average, these other six. Right? Spock, that average, is about 14, so I don't need that. Right? So what's the standard error for this contrast? Right? In general, is where we can take a contrast, I'll just call it L, where we take different, I guess L for linear, really. We can look at some contrast in the means, where the AIs are some multipliers on there. And we're going to estimate that contrast by putting in the y bar i's for the different groups. And so under our ANOVA model, what's the variance of this thing? Well, since the groups are independent, we still have a sum. And the AI is a number, a multiplier. When we're taking just the difference of two means, there can be a +1 and a -1. Take a great difference. But AI would get squared here, and then we have the variance of the y bar i's. And so the variance of y bar i's have a sigma squared in it. AI squared. And there'd be a 1 over n sub I that's in here. And so to estimate the variance, a little hat over that. So estimated variance is we're going to put the mean square error in here as our estimate of sigma. And we're going to use degrees of freedom. That was our n minus I. Right? And so for different contrasts that we might be interested in, we can estimate the variance. Right? One example of a contrast is just a difference of means. Another type of contrast is like the average of the other ones minus the average for Spock. And so you could do these, 2 diets versus 4 diets, right? Is there a difference in those groups? So, just to write out real quick as an example. So you want to do mu1 minus mu2. you could have contrasts. The AI contrast could be 1, -1, and then zeros for the others. So the contrast, if you do the sum of the AIs times the mu sub i's, is effectively here going to produce mu sub 1, minus mu sub 2. So just a difference of means depending on where you put the 1 and -1 you get. In this case with the Spock, I'm going to use A values that are 1/6, 1/6, 6 of it, 1, 2, 3, 4, 5, 6, and -1. So this is going to produce the average of mu1 plus mu2 plus mu3 plus mu4 plus mu5 plus mu6, right, over 6, the average of all those, minus mu sub 7. And I'm going to put the sample means in there to estimate it. And so anyway, it fits within this broader thing of looking at those. So we're just going to test that one hypothesis. Is Spock different from the average of these other people? So I've got the others average of 29 and Spock's average of 14. This is the standard error formula. Right? The standard error ends up being 2.64. And the t-value we get to use for confidence intervals in testing is 2.02. And so if we do others minus Spock plus or minus a margin of error, we get an interval that's 9.6 up to 20.9. So that's the difference, like the average difference between other ones, other trials, and Spock's trials appears to be somewhere between 9.6 and 20.3% in terms of percentage female. So it doesn't include 0. It looks like a lot different. If we wanted to do a t-test statistic, we could take the observed difference between the average of the others and the mean for Spock divided by that same standard error, and that t-value is 12.6. So a t-statistic of 12.6 is way off the charts. It's a lot bigger than our 2.02 certainly, and we would conclude that there's a significant difference, right? That it's not just chance. There's, for some reason, his is a whole lot lower. For this, I would say that you wouldn't really have to do any type of multiple adjustment, right? Because if you have one hypothesis, it's fine to do that. I think the traditional thing would be to test with an ANOVA. Is there any difference at all? Right, and then test a specific contrast. And it's okay to do that, the overall test of any difference, and then kind of one focused one, if that's what you're really interested in. In this case, even if they said you had to adjust, I don't know why you would have to, because you have one focused hypothesis to look at, but if they did, it'd still be significant because it's such a huge difference. Right? But that's the idea of contrast in multiple testing. And once you get a significant result from that, then you look to see where it is and to describe it. Right? And maybe you look at all means. Maybe you have a scientific hypothesis to give just a few tests. But often there's a desire or a requirement to account for how many different things you're testing, and not just to report whatever looks biggest and claim that that's a significant result just because it's sticking out. If you did 1,000 tests where there'd be nothing going on, there'd be an upper 2.5% and a lower 2.5%. And if you called those significant, that would just be by chance. If you repeated it and did a test again, there'd be no guarantee that that group would be the biggest if in fact there was nothing going on. Adjusting for the number of tests, right? If it's significant after you adjust for that, the idea is that the next time you would do that testing of that group, you would expect to get a significant result again, and that it's not just due to chance because it's past a stronger test. So great. That's what we'll do on Friday. We'll take questions about this? I know it kind of went a little fast there for part of the contract business. If you haven't turned in the homework, pick this one up. Another homework will go up pretty soon with a little more ANOVA computer.
Thank you.
Yes. Okay. Oh, I didn't stand down. Yes, yes, yeah. I'll be down in my office. That'd be fine, thanks.